Hello everyone. Today I'm going to start by correcting the homework that I had assigned you on the handout from the last time, just so you can see different questions being answered, and if you did attempt them, make sure you got the right answers, and if you have any questions, you can email me your questions so that I can clarify anything that you might be having trouble with. So, we're dealing with theoretical probability. First question says, find the probability of each of the following situations. Draw the event tree if needed. So we toss a coin. What is the probability of seeing tails come up? So if I draw my coin here, there are only two possibilities. And that's heads or tails. Okay? So the theoretical probability of seeing tails come up from our formula the other day is equal to the number of successes over the total possible outcomes. So what are our number of successes? Well, our number of successes would follow the branch that we're talking about, which is the tails branch. So there's one possibility of a success. And what is our total? Our total is 2. There are 2 possible outcomes in this experiment. So the probability of getting tails is 1 over 2. To write that as a decimal, we just divide 1 by 2. 1 divided by 2 is 0.5. And to write it as a percentage, we would then just write it by multiplying by 100 to get our percentage. I'm going to actually write that under here so you can see how that happened. So we multiply by 100 to turn it into a percentage. Question B is related to question A. It says, what happens if you toss 2 coins? What is the probability of seeing both coins show tails? So, just as I mentioned before, the probability that would arise from tossing 2 coins is actually the same as the probability that would arise from tossing 1 coin twice. It's the exact same event tree. So we already have our first event tree here of tossing 1 coin, so we're just going to copy that again. And now we're going to do the next part of the tree, which is, well, after we've tossed the coin and gotten heads, what are the other 2 possibilities once I toss the second coin, or if I toss the first coin twice? So the tree would be the same. We get heads and tails, and for the first time getting tails, we would also get heads and tails on our second toss. So I just want to show you how you could build this as a table instead. And I had shown a full table the other day in the lesson, but you can actually, make your work a little bit faster if you don't actually draw the entire T-chart like I showed. You can just start by saying, well, we can get heads and then tails. We can get heads and then heads. We can get tails and then heads, and then tails and then tails. So these 2 different ways of showing what happens are equivalent. Okay, some people like this one, especially when there's a lot more to the tree, and I might show that example down here because it's not that the tree is difficult for this one, because there's only 2 possibilities, but with a die roll like I showed the other day when there's 6 possibilities, this can get really long and hard to draw. You might run out of space. So using a table like this can save a little bit of space, and it does the same thing. So it's asking, what is the possibility of seeing both coins show tails? Well, in the tree, that would be down this branch here. In the table, this would be that branch. Okay, so that is one possibility. So again, our probability of tails tails, we have one possibility out of what total? Well, if we look at the tree, we have a total of 4. If we look at the chart, we also have a total of 4. So in both cases, we would get 1 over 4 as our number of successes over a total number of possibilities. And 1 over 4 as a decimal, 1/4, if you think of money, is 0.25. And multiplying by 100 gives us 25%. So where there's a 50% chance of getting heads or tails, there's only a 25% chance of getting double tails. And in fact, there's a 25% chance of getting heads or tails, heads or heads, tails or heads, or tails or tails. It's the same probability for each one of these cases. So what if we toss 3 coins? What is the probability of seeing only one tail in all 3 coins? So again, tossing 3 coins is like tossing 1 coin 3 times. We start off the exact same way as question B. And then we just do one more line of branches. So this is our first toss, this is our second toss, and this is our third toss. So heads, tails, heads, tails, heads, tails, heads, tails. So you'll notice that there's now 6 possibilities. And just to start thinking about the math behind these trees, there are 2 outcomes and 3 trials. It kind of looks like 2 times 3 gives us the answer 6. Let's see if that works out above. 2 outcomes, 2 trials, 2 times 2 is 4. So it kind of looks like there's a pattern there. I'm not going to tell you whether or not that's an actual pattern. You can either look it up, or as we continue on we might discover it, but it does kind of look like there's a pattern there. Okay? So just to show you now what the table would look like, if I just separate this. So for the table, what you want to do is try to write down all of the combinations of having 3 different trials. So there's going to be 3 coin tosses. And let's start with an easy one, where you get heads the first time, heads the second time, heads the third time. Well, what I'm going to do is I'm going to one at a time change the different columns to get all of the different combinations. So heads, heads, tails would be one combination after that. So we just changed this one. And then we could get heads, tails, tails by changing this one. And then we could get heads, tails, heads, which we haven't done yet, right? So we changed this one back to H for heads to show that other combination. So we've gotten 4 combinations where we started with H, changing one column at a time, and making sure that we've hit every combination where there's an H in a column and a T in a column. Okay? And that's starting with H, but now we have to do the exact same thing with tails. So if I start with tails, 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 I could do tails, tails, heads, changing the last one. So I'm basically following the same pattern I did here. So then I'm going to change this one to heads. And then I'm going to change the last one back to tails to make sure I get that one. And then I've got all my 4 again. So for tails. So this, each one of these rows follows a branch. HHH is here, HHT, HTH, which I have here, and HTT, which I have here. So I didn't do them in exactly the same order as the branches, but I made sure to, by changing one at a time, and you never want to change two at a time. It's kind of like those word puzzles where they give you like 4 letters, and by changing one letter at a time can you get to a completely different word. It's kind of the same thing, same idea. So this is, some people prefer this to the tree, just because the tree starts to get bigger and bigger. And like I said, especially if you have like a multiple, like a die roll, you'd have 6 columns here. That could take a while with the tree. It would take a while with the table too, but it might be a little bit easier to follow. So we haven't answered the question yet. So you toss 3 coins. What is the probability of seeing only one tail on all 3 coins? So let's circle all of the scenarios where we only have one tail. So HHT. So I'm just going to circle the bottom one instead of the entire branch. Okay, but this would be the branch that gives just one tail. Coming down here, this would be the branch. There is one tail right there. Okay, so this would be the branch that gives one tail. This branch gives 2 tails, so that one doesn't count. Starting up here, tails, heads, heads. So this branch has only one tail. Tail, heads, tails does not. And this one can't, because right away there's 2 tails, so none of these work. Over here, we can see that this one has one tail. This one has one tail. And this one has one tail. So we get the exact same result. So our answer for the probability of one tail is 3 out of 1, 2, 3, 4, 5, 6, 7, 8 different possibilities. So now that probability I'm going to have to use a calculator to figure out. So let me just switch over to the calculator here. There we go. I think you should be able to see it now. So 3 divided by 8 gives 0.375. And then, so I'll just write that down, 0.375. And as a percentage, that would be 37.5%. So there's a 37.5% of getting only one tail on all 3 coins, which is higher than getting 2 tails in a row on 2 coins, or 2 coin throws, but lower than getting just a heads or a tails. So it falls in between those two. So there's an example of using theoretical probability and a event tree or an event table to figure out the probability of a scenario like this. So for letter D, it almost looks like the exact same question as before. It says you toss 3 coins. What is the probability of seeing at least one tail on all 3 coins? But the difference with this question is it says at least one tail. So if I go back to this question here, for C, it said seeing only one tail. Sorry about that. Seeing only one tail. But the next one says at least one tail. So if it's saying at least one tail, that means it can actually be more than one. Okay, you could have 2 tails or 3 tails. So at least means one tail has to show, but you can have more. So what is the probability of seeing at least one tail? Well, what we're going to do is we're going to circle every row that has at least one tail. So this row has at least one. This one has at least one. It has 2, but it has at least one. This one has at least one. This one. This one. And in fact, all of the rest all the way down. So we have 1, 2, 3, 4, 5, 6, 7. So the probability of at least one tail is equal to 7 out of 8. And if I switch over to my calculator again, what is 7 divided by 8? That is 0.875. So 0.875 is my decimal answer. And the percentage multiplying by 100 moves the decimal 2 spots would be 87.5%. So be careful when you read sentences. If you see words like at least, you have to understand that that means there can be more. If it says only one tail, that means only one, but at least means multiple. So our next example here, find the probability of this situation when we're rolling a 6-sided die. So what is the probability of rolling a 5? So this is just one die. We've actually seen examples of this in class. When you have one die, there are 6 possibilities. 1, 2, 3, 4, 5, 6. So the probability of rolling a 5 is 1 success out of 6. We've already seen this in class. So I'm going to let you figure out the decimal and percentage versions of this number. And like I said, we've already done it in class. So that's part A. Part B says, what is the probability of rolling a 1 or a 2? Well, if we go back to our tree, that would be 2 successes, a 1 or a 2. We would actually, I'm not going to circle it so I'm not interfering with this question, but we would actually circle the 1 and the 2, which means it's 2 out of 6 chances. So the probability of rolling a 1 or a 2 is 2 out of 6 chances. 2 out of 6 is 1/3. If we reduce this fraction by dividing both the top and the bottom by 2, that gives us 1/3. 1/3 is 0.33 periodical. And multiplying by 100 gives us 33% approximately. Actually, I'm not going to put the dot there, sorry. Approximation. We are rounding the number off, and I know probably the periodical should go here instead, but I wanted to have 2 decimals to show you that when you change it into a percentage, you really probably should have 33% there. So there's a 33% chance of getting a 1 or a 2. What is the probability of rolling an odd number? Well, once again, if I go back to the event tree, what are the odd numbers? 1, 3, and 5. So there's 3 odd numbers out of 6. So our successes would be 3. Our total possibilities is 6. That gives 1/2, which is 0.5. Sorry, it gives 1/2 because these 2 are divisible by 3. I should probably write that in. So we can reduce the fraction. And multiplying by 100 moves the decimal place 2 spaces, so that is 50%. So there is a 50% chance of rolling an odd number on a die. What is the probability of rolling a number greater than 2? Well, what are all the numbers greater than 2 on a die? We've got 3, 4, 5, 6. So the probability of rolling greater than 2 is equal to 4 out of 6. 4 out of 6 can also be reduced. That gives 2/3. And since 1/3 was 0.33, 2/3 is the double of that, which is 0.66. And writing that as a percentage gives 66%. So there's a 66% chance of rolling a number greater than 2. So hopefully you're starting to get a better feel as to how to set up these questions. You could always rewatch the videos. Let's skip to the next question. Now for the next question, we're going to be dealing with a standard deck of cards. I'm not sure how many of you have played card games. It seems that card games aren't as popular as they used to be before, but they are still played quite a bit. Solitaire, for instance, is a game that a lot of people play, or euchre. So a standard deck of cards contains 52 cards. These are all of the cards in the deck. So there are 4 suits. Okay, so each one of these is called a suit. And each suit has 13 cards. And I've listed the name of the cards here. So clubs and spades are the black cards, diamonds and hearts are the red cards. So this is a club, this is a heart, this is a spade, and this is a diamond. Okay? So it says, based on the above description of a standard deck of cards, calculate the probability for the following situations based on an experiment of drawing 1 card from a well-shuffled deck. Now, even though this is an experiment, we are talking about the theoretical probability here. Okay? The experiment is just saying, what is the theoretical probability of drawing a specific card if we draw 1 card out of the deck? Okay? So, what is the probability of drawing a red card from the deck? Well, what are our number of successes? How many red cards? What are our number of successes? Well, how many red cards are there in total? Well, if there's 13 cards of each kind, that means there are 26 red cards in total. And we know that our probability formula is a division of our number of successes divided by our total number of possibilities. So the probability of drawing a red card would be 26 out of our total number of cards, which is 52. And both of those numbers are reducible because 26 divided by 26 works, and 52 divided by 26 works. And that will actually give us a 1/2 as our probability. We've already seen 1/2 a couple of times. That means that if you draw 1 card out of a deck of cards, you have a 50-50 chance, or 50% chance of drawing a red card, which actually means you also have a 50% chance of drawing a black card, because the numbers here would be the exact same if we did a black card. What is the probability of drawing a heart card from the deck? Well, if we go back to the picture of the deck, how many heart cards are there? Well, there's 13 heart cards. So the probability of drawing a heart is equal to 13 out of 52. Just to check, if I'm not mistaken, I believe 52 is divisible by 13, as you can see. Now, technically, why wouldn't I not have needed my calculator for that? Well, I wanted to show you on the calculator, but it should be pretty clear that there are 4 groups of 13 in a deck. There's 13 here, 13 here, 13 here, 13 here. So 13 has to fit into 52. In other words, 52 has to be divisible by 13 because there's 4 groups of 13 that make up 52. So sometimes it's not necessary to jump onto a calculator right away. So, oops, wrong color, sorry folks. So we can divide this by 13. We can divide this by 13. that gives 1 over 4. We've also seen 1/4 as a decimal and a percentage, so I'm not going to go over and explain how that becomes those numbers. So there's a 25% chance of drawing a heart from the deck. And is what is the probability of drawing an even card of any suit from the deck? Well, how many even cards are there? 2, 4, 6, 8, 10. And we're not talking about the queen here. So technically the queen would also be an even card, but I'm only talking about the numerical cards, not the face cards here, okay? And usually the question will be a little bit more specific than that, but because I just forgot to mention, we're just talking about the even cards. Well, they're all above each other, right? So there's 1, 2, 3, 4, 5 even cards for one suit, but there's 4 suits. So there's 20 times 5 even cards. Or I'll write 5 times 20. Sorry, not 5 times 20. 5 times 4, which is 20 even cards. I messed myself up there. I'm just going to make sure that's right. So again, 1, 2, 3, 4, 5 even cards. 5 times 4 is 20. So our chance of success, or our number of successes, is 20. Our probability of drawing an even card, therefore, is 20 divided by 52. Now, 20 does not evenly fit into 52, but both of them are at least divisible by 2. So let's just do this rigorously here. So if I divide both of these by 2, I'm going to get 10 over 26, which means both of them are again divisible by 2, which actually means I could have just divided by 4, but if you're not sure how to simplify, sometimes it's easier to just do it in multiple steps, which is 5 over 13. 5 over 13 as a decimal. Let's go back to our calculator. 5 divided by 13 is equal to 0.38. 0.384, but we'll just round it to 0.38. And that is 38%. Now you'll notice that 5 out of 13, if we go back to our deck of cards, that's just 1, 2, 3, 4, 5 evens out of 13 of any one suit. And this is just how fractions work, right? It's a proportional statement. So 20 out of 52, it's the exact same thing as 5 out of 13. So you could have just thought of how probable is it to pick an even card out of one suit, and that would be the probability of picking an even card out of the entire deck. Okay. What is the probability of drawing a face card from the deck? Well, if we go back to our deck of cards, we have 3 face cards per suit. So 3, 6, 9, 12, or 3 times 4. So the probability of a face card is 12 out of 52. And some of you might be already understanding that there's another way of doing this based on the previous example. So both of these are divisible by 4 again. So just like this one was divisible by 4. So we know that 52 divided by 4 is 13. We know that 12 divided by 4 is possible as well. So we end up with 3 over 13. And if you look back at our deck of cards, there are 3 face cards per suit. So again, because it is a proportional ratio, figuring out the probability of picking face cards out of one suit is the exact same thing as figuring out the probability of picking a face card from the entire deck. I'm gonna let you figure out the decimal and percentage values of this one. Okay, so this is an example right out of your textbook, and it says Jason, Tony, and Lisa have each won a video game from Ace Video Games Inc. as part of an advertising promotion. The video games, Extreme Racing, Golf Legends, and Hoops, will be randomly assigned to the 3 winners. What is the probability Jason will receive Golf Legends? So in this case, they're basically asking you to set up a table. Let me go back here, similar to the one we did for the coins. The coins here. Okay, so we just want to take a look at each possibility of winning the games in a specific order. So let's call Extreme Racing X, Golf Legends G, and Hoops H. Okay, so what are all the different combinations of those 3 letters that can be given to Jason, Tony, and Lisa? Well, I'm going to start with X. And now this is a little bit different because you can't repeat X. Tony can't win the same game. So we're just going to cycle through all the possibilities of these 3 letters. So this one's a little bit different from the coins because you can't repeat any of the letters. Okay? So we started with X. We can get G and H. We can get X and H and G. So that's the only 2 combinations that you can get starting with X. So then we're going to start with G. Well, with G we can get X and H, and with G we can get H and X. Now we have to finish with H as our first letter. With H we can get X and G, and with H we can get G and X. So all I'm doing is cycling through all 3 letters, using 1 letter at a time as being the first letter of the cycle, and then changing the order of the 2 other letters. And that gives us all of our possibilities. So what is the probability Jason will receive Golf Legends? Well, where does Jason receive Golf Legends? Well, Jason is here. Jason receives Golf Legends here and here. So there are 2 successes. Jason gets golf. So there are 2 successes over a total of how many? 1, 2, 3, 4, 5, 6. So our total of 6. Both of these are divisible by 2, which gives 1/3. We've already seen 1/3 is 0.33, which is a 33% chance that Jason will get Golf Legends. And I could ask the question, what is the percentage of Lisa getting Hoops? Or what is the percentage of Tony getting Extreme Racing? So I could also ask the question, what is the chance of Tony not getting Extreme Racing? So if I asked a question like that, you'd actually have to look at all the cases where Tony doesn't get Extreme Racing, which would be 1, 2, 3, 4, which would be 4 out of 6 chances. So you can ask quite a few different interesting questions with probability. So I've actually already done number 2 with you here. Here's a reflection question. I know it says number 4 here, but we actually did number 3 together already. So I'm just going to skip that. Another way to approach the problem is to consider the number of different games and the fact that there is an equal chance of getting each of them. Explain how this approach will lead to the same result as when we considered the arrangements. So I'm going to let you think about that, looking back at the previous question. Just think about what that could mean and how that could help us solve the problem. So that's going to be it for today's lesson, folks. I will be posting some homework questions from your textbook. I'll put a link to the, or I'll tell you what section of the textbook to look at in the link that's in the Google Classroom. And we will look at some of those homework questions in our next lesson. That's it for today. We're going to stop there. If you have any questions, either doing the homework or doing or reading or looking through this video, please email me and let me know, and I'll try to explain it a little bit more in detail to you. Have a great day, everyone.